We'll go from current slide. And let me hit the announcements first. I think I told you all this before. The error in here doesn't affect this class any, but it may affect you in other classes. They came out with this exam schedule a week or so ago, maybe a little longer, and I didn't notice it at first until I noticed that the academic calendar, the administrative calendar, all the calendars I've seen say finals start on Tuesday the 30th. And this says they start on Monday the 29th. So if you have a Monday, Wednesday class that has a final, check with your instructor and see. This, I think, is wrong. I think it's supposed to be finals, according to those other calendars, go from Tuesday till the following Monday. So this, I think, is wrong. Of course, it doesn't affect us because we're a mini-term class and we're a Tuesday, Thursday class. But talking about that then, because we're a mini-term class, we don't follow finals week like the others do. We have class the Tuesday, April 30th, even though that is the first day of finals. We have class that day. Thursday, the May 2nd, that's when our final is. Okay, so we have regular class on Tuesday 2nd. So we have class today, class next week 2 days, and then Tuesday of the following week. Now, if we need to, technically they said our final exams, I don't like this, I don't believe in it, is Monday, May 6th for all second mini-term classes. Well, if you're taking more than one, that means you have a bunch of finals on one day, which I don't like. Number two, for people who are working, and Tuesday, Thursday afternoon is when they have off to come to class, to ask them to come in for a final on Monday, at what time, we don't know. You know, that's sort of nuts too. And what if you had a Monday, Wednesday class in the afternoon and Tuesday, Thursday in the afternoon? The finals would be at the same time. So that doesn't make any sense. So I'm planning to give our final on Thursday, whatever day that is, the 2nd, and that's when ours will be. Now, are you graduating this term? No. Okay. Anyone who is graduating this term, you have to take your final on Thursday because your grades are due on Friday at noon. So I need to know if you're graduating because as soon as you finish everything, I've got to get those grades in for you by Friday at noon. Okay. End of the term gets a little crazy. Okay. So where does that leave us? Well, here's one place. With the last day of class being Tuesday the 30th, April 30th, that means on that day I'll be returning every lab and every test. So any lab not turned in by Tuesday the 30th, any test not completed by Tuesday the 30th is a 0. Okay, because I've got to return them that day, so you're having to study for your finals. Okay, so they have to be done by that day. I'd love to have them in sooner than that. In fact, I'd love for them to be in now so I can get rid of all those that I've been carrying around all term, but there's certain people, I'll go over it quickly. Uno, out of 20 students, one student has turned in a paper. And what did you just do? Okay, 2 now. Okay, maybe one more did earlier, but anyway, very, very few. And in lab 1, 2, 3 people haven't turned in lab 1. Test 1, 2, 3, 4, 5 people haven't done test 1. Lab 2, it just goes on like this. A few people in every, and it's not always the same people, haven't turned in the lab, haven't done a test. I don't have any of them. I got all that I could return them to you. So please get those in sooner rather than later so I can get them back to you sooner rather than later. Okay? All right. Oh, student course evaluations are open, and I hope you're doing them. Have you done them yet? Okay, please do them. Please, that's very valuable information for us. Okay. For me, especially as a department chair, I really need to see those things. Oh, and one more thing. This coming Tuesday, the 23rd, next Tuesday, Okay? Last day to withdraw from classes for first mini-term or term 2 courses. So in other words, if there is anybody, I don't think there's, well, there may be some who, well, I think everybody's been here some. There's 2 people who never showed, but they should have been removed from the roll by now. I don't know if they are or not. But anyway, of the rest, I think everybody at least has something turned in. But in other classes, if you're in grave danger of failing a course, it's far better to withdraw than it is to fail. Because withdrawing does not hurt you academically at all. Failing does hurt you academically at all. Withdrawal could mess with your student financial aid or something like that, but failing does too, the same way. So failing hurts your GPA, withdrawing does not. So it's far better to withdraw than it is to fail. Okay, so enough of that. Any questions? Oh, let's talk about today. Today we're going to do the first 2 hours, or what we got left of it, in Chapter 6. And I'm pretty sure we should get pretty far along, at least through all the electricity part, and we should get into the magnetism part today. Okay? We probably won't finish the chapter because we're only going to be 2 hours at it, but we will get pretty far along. So that's today. Next 2 hours is going to be the second lab in electricity. This will be Ohm's Law lab. And that will be down here, hopefully in this lab here, but if not, across the hall. If not that, we'll be downstairs. We'll be somewhere, but hopefully 253. Okay, then the last 30 minutes today is a test on Chapter 4. We finished that last time, so the test for Chapter 4 will be today, the last 30 minutes. Okay, now where does that put us in the future? Okay, next Tuesday, we should finish Chapter 6 and be ready for the lab in Chapter 6. So that'll be 2.5 hours of class, and we're going to get started in Chapter 8, and then we'll stop and have the last lab in Chapter 6. Thursday, we'll continue in Chapter 8, probably not have a lab, but we will have the test for Chapter 6 on Thursday. And hopefully then we will have finished or gotten close enough to finish Chapter 8 on the following Tuesday, which is the last day of class. It's also the day I return all your papers to you. And that's also, we'll finish the Chapter 8, and then we'll have the lab on Chapter 8. All right. Now, at that point, I'll give you all the option. Anyone who wants to take the Chapter 8 test on Tuesday, if we have time, and I think we will, knock on wood, we'll see. If you want to take the Chapter 8 test that day, the day we finish it, if you want to try to do that, you certainly can. I think you'll have time to do your formula equation sheet and all that kind of stuff. And if some of you want to go and take your final that day too, I'll try to have it ready, both the last test and the final. But neither of those are due until the Thursday, and that's when technically they will be. Okay. So, any question on how we're going to wind this up? And please do the student course evaluation. Okay. All right. We got down to, and I don't, actually, let's go see what the previous slide was. There is a little bit here. The figure here, I think we talked about last time, but we didn't sort of follow up on it with the more current details because the slides in the book weren't quite matching all that well here. But there's an illustration. I wish they showed it here. At the top of page 151, the left-hand column, and it's of an automobile. Okay? And it's referring to this thing. The drift velocity of electrons is incredibly slow. It's not like you do a switch and these electrons rush down the wire and then do the work. They don't. There's no rush to it. They bounce along and bump into other things, attracted by protons or whatever, and they follow a very tortuous route. Sometimes even going backwards a little way. It's a very, very slow process, the drift velocity of electrons. The electric field, on the other hand, is instantaneous. You hit the switch, and all the electrons within the whole circuit, they feel the electric field almost at the speed of light. That fast, almost instantaneously, so they all start moving. And that's why the lights come on. That's why you don't see a delay between the flicking of the switch. And here was the example at the top of page 151. You have a car, and we've doubled the class size. Way to go. And so far I have all Y chromosomes, so I don't know where the X's are today. Hopefully they'll get here. Seth is here. Okay. One thing that I haven't been saying a lot, have you done the student course evaluations yet? Okay, do them sometime, so don't forget them. Okay, you can wait till you see the final or whatever. Please don't forget to do them. Okay, but we're talking about this one. We're talking about how slow the electrons actually travel. The illustration on the top of page 151 is an automobile. And somewhere in the cabin of the car, there's a brake pedal, right? And when you press on the brake, you start stopping, but your brake light comes on, right? Or you hope it does, right? Because the cars behind you need to see that you're braking. Well, if you are waiting for the electrons you press the brake pedal, it sends the signal to the battery, which is in the front of the car, and then it's about 2 meters to get to the brake light. Okay? 2 meters. That's not far. I'm about 2 meters tall, right? A little bit less than 2 meters tall. This is about 2 meters, right? The doorknob is about 1 meter off the floor. Just double that, and that's 2 meters. That's about the length of the wire between the battery and the brake light. Okay? When you press the pedal and send the signal to the battery make the connection to the brake light, the velocity is about 1/100th of a centimeter per second. That is the actual drift velocity. When it says slow, it means slow. Okay. 1/100th of a centimeter. Okay? Take your little fingernail. Now, don't do this, just imagine doing it. Slicing it into 100 equal slices. That's pretty small. Wait. Let's get even better than that. Even better than that. I had it out and I put it back in. Let's take a dime. A dime is 1 millimeter, which is 1/10 of a centimeter. Take that dime and slice it into, you can do this if you want to, into 10 equal slices. That's how far the electron travels in 1 second. That's pretty slow. And at that rate of speed, it would take, and you got 2 meters, which is 200 centimeters to go, that would take more than 5 hours for the electron in the battery to make its way to the taillight. That's increase the class size by 50%. Good deal. Brett is here. What's that? Yeah, there is a test today, Chapter 4 test. Okay. That's why I'm surprised there's not more people here. Okay, but we're just talking about if you are waiting for the electron to leave the battery and get to the brake light, if you hit the brake, at the rate that travels, it would be more than 5 hours for that electron to get from the battery to the brake light. It's not that. It's the field is almost instantaneously. As soon as you hit it, the field is set up throughout the circuit, and the electrons right near the brake light, they're the ones that are moving. That gets the brake light to come home. The others are all moving too, but they're incredibly slow. It's the field that counts, okay? Not the movement of electrons. So therefore, who cares what charges are moving? They're all moving awfully slow. All right. That was the last thing I wanted to talk about that we didn't have time to. Last time we ran out of time. But at the top of page 151, top of the right-hand column, there's a little blurb, mistakes and misunderstandings on what is electricity. And it says it's a misunderstanding that electricity is electrons moving through wires at nearly the speed of light. No, we just saw they move at a tenth of a thickness of a dime each second. Okay, that is slow, really slow. Okay, you can read the rest of that. It's real well worth it. All right, that leads us into electrical resistance. Okay, now when we had the circuits in there in the last lab, y'all remember that, right? What was making the lights come on? Okay, the battery was attached and we had the juice to it. So what were we using? Were you using the voltage that was turning the lights on? Was it the current that was turning the lights on? Was it what was it that was making the light come on? Okay, the voltage is almost correct, okay? Because what voltage is potential difference, and what that is energy per charge. That's what volts is. Joules per coulomb. It's the energy that was making it come on, supplied by the voltage. You're absolutely right, both of you on that. Okay? Energy per charge. Okay? That's what voltage is, but it was the energy that was making the light come on. We weren't using up coulombs of charge. No. Same coulombs that left the battery came back into the battery. You didn't use them up. You used the energy that the battery had given the charge. Okay? Now, two sources of the loss of the energy. One is collisions with other electrons in the current, okay? And the other is collisions with other charges in the material. And if you went back to this figure we looked at before, this one, it shows these electrons really bumping into protons because they're attracted to them. They're going to bump into them, okay? Or positive charges or whatever. And then they bounce around, okay? Occasionally they'll bump into other electrons. They really don't want to because they're both negative charges, so that may slow them down. That's why sometimes I said they may actually move backward. If they bumped into an electron, they're going to go the opposite direction, okay? So, the second is, one is collision with other electrons, others are collision with other charges in the material. Okay? Now, a guy named Georg Ohm came up with this rule. He noticed that the voltage was proportional to the current, and the current proportional to the voltage. Remember we did that in Chapter 1, proportionality. To make it an equality, an equation, we put a constant. Well, his constant of proportionality was later called resistance. That's what was the constant proportionality between voltage and current. Increase the current, you increase the voltage. Increase the voltage, you increase the current. Usually increase the voltage, increase the current. Okay? So that constant proportionality was the resistance. Now, the work was done by Georg Ohm. O-H-M was his last name, German physicist. Okay? So they decided to name the unit after him, ohm. Now, what symbol would they normally use for ohm? Ampere uses A. Volt uses V. Capital V, because it's named after someone. What unit would you think they would use for ohm? Okay, they use that, but why? Why didn't they use capital O? They used capital C for Coulomb, for Charles Coulomb, capital A for Ampere, for goodness, I can't think of his name now, Luigi, whatever his name was, Ampere, that wasn't it, whatever it was, volts for volt, capital V. Why didn't they use capital O for ohm? Any ideas? Well, what if we had name a size of a resistor? So many ohms. Give me a number. Second?
1.5 kilohms.
1.5, you said? I can't hear.
1.5 kilohms.
Okay, let's just do 1.5 ohms to start with, okay? Very small. Let me get my pen set up. So what if I was trying to do 1.5 ohms? Is that a good unit? What's wrong with that picture? It looks like 1.50, doesn't it? They couldn't use a capital O for ohm, okay? So what did they do? They went to the Greek alphabet. But in the Greek alphabet, the letter that corresponds to O in the English alphabet is Omicron. And guess how it looks? Like an O, okay? It wouldn't work either. But in the Greek alphabet, there's actually two Greek letters that start with O. The one that corresponds to our O is Omicron. That looks just like our O. But the other one, at the very end, the very last letter in the Greek alphabet is Omega. So its symbol, its capital symbol, is that. That's where we get it from. The Greek symbol, capital Omega. This isn't a little omega. A little omega looks like this. It looks like a W, but it's rounded and it sort of curls up. That's a little omega. They capitalize it because it's named after somebody, and that's it. Now, before we even get to Ohm's law, just want to tell you a dumb story about how crazy physicists are. Just sort of weird-minded, okay? There is another thing that they like to measure. This is resistance. There's another thing that's called conductance, okay, which is how easily something. See, resistance is the thing that resists the motion of the charges through the wire. That's resistance, okay? Well, the ease with which they go through the wire, that's called conductance. So they needed a symbol for conductance. So what do you think they would name a conductance, the unit for a conductance? They first have to have something to call it. What do you think it was called? By the way, it's the reciprocal of resistance. 1 over resistance is conductance. So what unit would they use to measure conductance? Anyone have a guess? A mho. Now, does that mean that Mo, the partner of Larry and Curly, came up with this? No, that's not what it meant. Who named Mo? Was there anyone named Mo? No, no Mo. Is what? I can't hear.
They just flipped the letters.
That's exactly what they did. This is how crazy physicists are. Rather than giving naming it after someone, they just wrote ohms backwards. And I'm serious. They wrote ohms backwards. So if you had so much conductance of material, you'd measure that in mohs. Okay? Now, what symbol are they going to use for mho? They can't use M. That's already being used for meter. No, the lowercase omega is used as a frequency parameter. Okay? Angular frequency parameter. So no, they didn't use that. Any idea what symbol they could use for mohs? M's are already used. Capital M's are already used. It's just, they're all over the place. Here's what they use. They flipped it over. It's reciprocal. So that's the symbol they use for mohs. Boy, are physicists ever crazy. Who would think of doing something like that? I don't know. Okay. Anyway, this came up being Ohm's law. V, voltage is equal current times resistance because of the relationship, the proportionality constant between current and voltage. Okay? But you could write this one other way, and here it is. Divide both sides by R, and you get I is equal to V over R. Now you see that current depends on voltage. We already knew that. And that's directly proportional, but it's inversely proportional to resistance. If the current goes up, the resistance must have gone down. If resistance goes up, the current has to go down. So those are inversely proportional. There's one other form of Ohm's law you could write. Can you tell me what that would be? Second? No, we haven't gotten to power yet. We're still on Ohm's law. One other way to write the same thing. Say, R is equal to V over I. Perfect. Okay? Now, have y'all ever done the triangles or circle to help you remember how to put those together? You know what I'm talking about? Okay. And either one of them works. Some people, I like the triangle. Well, that's not a very good looking triangle. Do a horizontal line and a vertical line. Vertical line is a multiplication line. Horizontal line is a division line. Put the thing that is by itself, V on top, and put your I and your R down here. Okay? Then if you're wanting to remember this, voltage is the current times resistance. That's what we've got here. Current is equal to voltage divided by resistance. That's what we've got here. Or resistance is equal to voltage divided by current. That's what we've got there. And you could do the same thing with circles if you prefer circles. Do a dividing line and a multiplication line. Okay? Put the V on top, the I here, and the R there. So either way you do it, it's the same thing. It's just whether you like the triangular shape or the circular shape. It doesn't matter. So many of our formulas in physics are related in this way. You can do lots and lots of formulas that way. The power formula we're going to get to a little bit later, done the same way. Okay? All right, so that's electrical resistance. Okay? And we've already mentioned the units. 1 ohm is equal to 1 volt per 1 amp. So an ohm is the amount of resistance. If you have a 1 volt power supply and you get 1 amp of current through it, that means you have 1 ohm of resistance. Okay? That's how we define an ohm. Okay? Any questions? Now, that form, any one of those 3 forms, represents Ohm's law. Now, there's a little something else we can do with Ohm's law. Not with Ohm's law, but about resistance. And here's what it is. There's different things that contribute to resistance. Okay? One is a type of material. Copper is a great conductor, so it has very little resistance. Silver is even better than copper. Very little resistance. Aluminum will work. It's not quite as good as copper. It will work. It's a good conductor. Gold is a good conductor. Not quite as good as copper, but a little bit better than aluminum. But then as you get on down, other metals are not quite as good. So the type of material determines the resistance. It's a resistance factor. There is a kind of material, it's called nichrome. It's a nickel chromium alloy. It's a conductor, but it's not a great conductor. And here's why. It just resists, and as it resists, it heats up and glows. You got an electric range stop on your stove at home? Or you got gas? Huh? The range spot, they put your pot on the board and
Oh, it's electric.
Huh? Electric. Have you ever noticed when you turn it on high, it gets real red? Well, you notice in the loud is dead on temperature. You know, that thing got hot, really red. That's nichrome. It conducts, but it offers a lot of resistance, so it really heats up. That strip that goes around the oven, you know, that thing around in the oven, that's nichrome resistant, okay? Not nearly as good as these others. If you had copper in there, it'd never get hot enough to cook anything, okay? Because it conducts too well. So the type of material is one resistance factor. Another is the length, okay? Now, sometimes give this as an example. I don't know if you've ever had this occasion. I had it at least once, and it wasn't a very pleasant one. there was a really serious ice storm over in Georgia, probably 5-6 years ago, sometime like that. And we have a little 2-bedroom bungalow over there that we go and stay when we go to the farm. Because when my parents died, the 4 of us inherited parts of the farm. And my sister lived in the house place. My younger brother lived in my grandmother's home. My older brother had as a mobile home on his part. We didn't have a place to stay, so we had to stay with one of them when we came. So we decided to go and put a little 2-bedroom bungalow up there. So we did, and in front of it were 4 big, really old pecan trees. Well, when the ice storm came, I mean, it broke so many limbs, and big limbs, small limbs, all sorts of limbs. The ground was just covered with limbs from those trees. Trees are still there. They're old trees. They've been through many ice storms before. But we had to clean them up. We cut the big pieces and hauled them off down into the woods. Nobody could burn that much wood. We didn't have a fireplace in our house, so we couldn't burn any of it. But we had a lot of sticks and twigs and other things left over. So we piled them up together, and we're going to burn them when they dried out some. And we did that, and before we did, I ran the hose from the house. Well, this first tree was way down there, so I ran it all the lengths of hose that I could get from all around the house. I still couldn't quite get to the fire, but I got close enough, so I was running water into a bucket, so if anything got out of control, I could put it off. Well, all those lengths of hose, and I turned on the water up at the house, and I asked my wife, I said, is the water running? She said, well, it's just dribbling. That's all it was doing, because the longer the hose, the more friction, resistance you had, so the water was coming out for it. Really good, because there was so much resistance in the hose, because of the length. Same thing is true with electricity. The longer the wire, the more resistance it has. Okay?
Well, it won't be the wire. The wires usually have 0 to 100.
Well, it depends on the type of material, too. If it's copper wire, it's going to conduct really well. But if it's one of those others that's not quite as good a conductor, it's going to have a little bit more resistance. So the length of the wire is a factor. Not a huge factor, but a little. Another is the cross-sectional area. If you think back to the hose again, if you put your thumb over the end of the hose, you cut down the flow, don't you? Because you're forcing the water through a much smaller area, and so you get less water out. Well, guess what? Cross-sectional area matters. And then the fourth of these is the temperature. The higher the temperature, the greater the resistance. That's because the molecules and the electrons, everything moves around faster with a higher temperature, so they bump into each other more frequently, and it retards the flow, more resistance in the flow. Now, y'all still remember what an incandescent light bulb looked like, right? Okay, you remember those. Nowadays it's more fluorescence, you see LEDs and stuff. But back in you're old enough, you can remember incandescent bulbs, especially the clear ones. Did you ever notice the filament in those? The ones you can see through? Describe it for me. Describe the filament. Yeah. Okay, yeah. And then what about the filament between the wires?
They usually have two prongs, like a little piece of wire or something.
Yeah, you think it. Little piece of wire. The thickness of that wire was just to make it a little bit thicker than hair. You got more than I do. You got the general idea, right? But what else about that filament? And a coil, wasn't it? Okay? If you really stretch that thing out, it would probably have been about that long. So what did you do? Okay, number one, let's talk back here. What was that filament made of? You probably don't know this. Second? No, not copper. Copper would have just conducted the electricity. It was never heated enough to give it wire. Who invented the light bulb? Thomas Edison. Thomas Edison. And he spent I don't know how long, trying to find the right material to make the filament out of. Finally, he landed on tungsten. I don't know if that's what they still use. I wouldn't be surprised if they didn't. But the type of material, tungsten, is way down in the conductivity range. Not nearly as good as copper or silver or gold or aluminum. It's way down there, maybe even less than iron. Not quite as low as thing. But what tungsten does, it has a lot of resistance, and then with that resistance, it heats up and glows. And that's what makes an incandescent light bulb come on. The glowing tungsten, or whatever the material is. So there's the type of material. The length was a really long length, and it's a high resistance material. Cross-sectional area is tiny. Really, really tiny. So there, the smaller the cross-sectional area, the more resistance. And we'll get the temperature in just a minute. So those three factors come together to give you the light bulb. And Thomas Edison had to play around with all those. How big the wire, how tiny the wire, how long the wire, he had to do it all. And here's three. Okay. All right, good deal. Thank you.
I spaced it out. I didn't try to do all that, but I did. It's in the back too.
Yeah, well, that's fine.
You got as much information about it, please.
Yeah, excellent. Okay. I stand corrected. That's a lot more papers in than I originally did. Recently, I only had one. Now several have come in. So sure enough, the electric light bulb, the incandescent light bulb, uses these three big types. Type of material, tungsten, not copper. Length, very long. They put it in the coil, so it would be a very long length. Cross-sectional area, they use a tiny, very, very, very thin wire. So it has a small cross-sectional area, giving it more resistance. And all that adds together to get hot enough to glow and give you light. Now, I haven't mentioned temperature with that. Let's include temperature now. I want your honest recollection of all the times in your life when the light bulb was blown out. When did it happen? You remember? Think of all the times the light bulb was blown out. When did it happen? Usually right when you turn it on. Absolutely. Not always. I've had light bulbs go out, they've been burning and then suddenly they go out. But most of the time it's right when you turn it on. What's that? When you turn the switch on. And why is that? Well, because the temperature of that filament, when you turn it on, is pretty close to room temperature, right? Pretty low temperature. Of course, as soon as it starts resisting the flow, the temperature goes up. Well, the higher the temperature, the more resistance. So therefore it glows, and it reaches equilibrium there. But when it's cool, it has lower resistance, so more current goes through, and the greater the current, the more likely it is to blow the filament. That's exactly why it glows most of the time when you first turn it on. Because the last time it was on, it was getting awfully thin, but it was hot, so it had a high enough resistance, didn't allow that much current to go through, okay? Because remember Ohm's law? The greater the current, the greater the current, the less resistance, the greater the current. So more current went through when it was cool, and it blew it, okay? But when it was hot, the resistance was larger, the current was less, not enough current to blow the bulb. So usually it's right when you turn it on. Okay. Now, there's another class of materials that is just really bizarre. And I would say of any one subject, this has to rate pretty high in the number of Nobel Prizes won in physics. Those people who have studied superconductors. You get negligible resistance, but it only happens at very, very low temperatures. Now, sometimes the materials are not all that great at conductors at high temperature, normal temperatures, but at very low temperatures, suddenly the resistance disappears. Those are called superconductors. And a superconductor, and by the way, this illustration shows the cross-sectional area. The bigger that is, the less resistance. The smaller it is, the greater resistance. length, the greater the length, the greater the resistance. And the material, it depends on whether it's a good conductor or not as good a conductor, and then the temperature of the material. So that's what we see. But negligible resistance at very low temperatures. Now, one of the ramifications of this is all you have to do is get the current moving, then you can remove the battery from it, and there's no resistance to use up the energy, so it just keeps flowing and flowing and flowing. Now, later we'll learn that the movement of charge is what creates a magnetic field. So therefore, in a superconductor, your charges are moving very easily and very quickly. They create a very strong magnetic field. The Japanese have used this, maybe others too, but I know the Japanese did, to build their high-speed trains. One of the things that keeps trains from moving any faster than they do is friction. You have friction between the track and the wheels, okay? Well, they use superconductors to create a very strong magnetic field, so actually the train sits up off the rail because that strong magnetic field forces it up. They're like charges, like poles. Forces it up, and then you have almost no frictional resistance. You still have some air resistance to make them very aerodynamic, so you minimize the air resistance. Those trains can go really, really fast. Okay? That might be a good paper topic, by the way, is how they use superconductors in their high-speed trains. All right. Now, let's go back one slide. Goodness, they don't give us any room, do they? Okay. We'll use this slide to do example 6.3. A light bulb in a 120-volt circuit. Okay, let's go back one more. Just do Ohm's law. Let's take some of this stuff off. All right, we'll use this slide. A light bulb in a 120-volt circuit. What's that a measure of? That's your voltage. The voltage is 120 volts. Now this is the one and perhaps only place you'll ever see it where the parameter is a capital V and the unit is a capital V. Most of the time the parameter and units are different symbols, but this is one they are the same. Okay? So 120 volt is switched on. The current of 0.5 amps. What's the symbol for current? I, capital I. I don't know where that comes from, by the way. If anyone does, that could be a good, huh?
Ampere.
Yeah, but that doesn't start with I. Where does the symbol I come from? I don't know. Okay, so the current is 0.5. How many zeros? 1? 50 amperes. Okay, flows through the filament. What is the resistance of the bulb? So we're looking for R. What would be the resistance of that bulb? You won't need it. I don't think so. Huh? Okay. How do you do it? What's the formula? No, you don't. Yeah. What is it? What divide? 120 volts. Huh? What goes on top? Okay, volts over amps, over current. Okay, which is 120 volts divided by current of 240. Perfect. Amps, and that would be 240 what units? Ohms. Okay, good. Okay, that's example 6.3. 6.4. What current would flow through an electrical device in a circuit with a potential difference of 120 volts? So there's your V is equal to 120 volts. Potential difference, that's joules per coulomb. Through an electrical device and a resistance of 30 ohms. So your R is 30 ohms. The question is what current would flow. So we're looking for what? Which is I. I is the symbol for it. It's measured in amps. Okay, and what's the relationship between current, voltage, and resistance? This should be pretty easy. What's the relationship? V divided by R. Right there it is. Okay, V divided by R. And the V is 120 volts. And the resistance is 30 ohms. And that would be for what? Amps. Perfect. Okay, 4 amps. And they don't put the 0.0, they just do 4. Sometimes they put it, sometimes they don't. 4 amps. That's how much current you get. 120 volts. Now, anytime you see 120 volts, 115 volts, 110 volts, even 90 volts, the odds are then you're talking about AC current. Okay, we're not making a distinction here, but you're talking about AC current. Because no battery that I know of can get you up to 90 volts. 9 volts is, pretty good. 12 volts in your car. I've seen some tractors that have 2 12-volt batteries, so those are 24 volts. I've actually heard of some bulldozers or things like this that have 3 12-volt batteries, so they get up to 36 volts. But I've never seen anything with 90 volts. Now, maybe a hybrid car does. I don't know what they have. But, if you're up to 120 volts, the odds are you're on AC by then. Okay. You can get high voltage on that. Okay. Now, enough said. Any questions about those? Electrical resistance. More on resistance. We already hit those. Now let's get to electrical power and work. This is something Brett was mentioning earlier. 3 circuit elements contribute to work. Well, we'll say 3. Well, this was also part of your lab, wasn't it? What do you have to have? You have to have a voltage source, a potential difference source, a power supply, a battery, whatever. You have to have something to give energy to the charges. Okay? That's your voltage source. You have to have an electrical device to use that. Your light bulb, your motor, whatever you're doing, that your device. And you have to have a pathway, your conducting wires to connect all those things together. That's to carry the current. Absolutely. Yes. Now, in order to use electrical power and do work, you have to maintain that potential difference across the device. That's why you have the voltage source in there. The input wire is usually at a higher potential than the output wire, because the input's bringing it in, the output's carrying it back. Are you carrying different amounts of current? No. No, you don't lose current. The current loses its energy. That's what's happening there. So the input wire is at the higher potential, output wire at the lower potential, and you've got the output wire is sometimes called the ground in AC currents, okay, circuits. We're not really going to do that much with AC circuits, but that's the output. No potential difference, there's no current, okay? And that's why even on high voltage wires, a bird can perch up there and not be damaged, because he's on one potential. The wire is a high potential, there's nothing at a low potential. Now if you were to throw up a metal strap and happen to touch the bird and it's touching the ground, yeah, he's fried, okay? Then there'd be a potential difference between the bird and the ground. But see, if he's up there on the wire, there is no potential difference. He's at that high potential, but there is no low potential. Okay. That's a rather strange place to put it, but it's there. Now, let's talk about power in circuits. Does anyone remember what the definition of power was? This was back when we did remember walking the stairs and that kind of stuff. What was power? It's what? Okay, you're jumping right ahead to what we're going to get to. But what was power originally when we first talked about it back in... Input. Second?
Input and your output.
Okay, yeah, we're getting to that too, okay? What was power back in the lab when we walked the stairs and ran the stairs? Second? Work done divided by the time. Remember, that was power. Power is work or energy divided by time. That's what power is. Okay? And what unit do we typically, SI unit, do we measure work or energy in? Joules. This would be a joule per, and what time? Second. Joule per second. We named that a what? Watt. You're right. It's a watt. A what? A watt. Okay. Okay. These are the units. These are the parameters. Power measured in watts. Work or energy measured in joules. Time measured in seconds. These are the parameters. Those are the units. A joule per second is a watt. Okay. Now, most of the time electrically, we don't talk about joules as our energy. And the reason for that, or my guess for the reason of that, when you use electricity, who sends you the bill? The power company, we call it.
Alabama Power.
Yeah.
You don't pay for electricity, you pay for power.
No, you don't pay for power or electricity. You pay for the energy you use. Not for the power, for the energy. And if you ever notice the bills,
just adds on.
okay, if you notice the bills, what are you paying for? Okay, yeah, you're paying for energy. How is it measured? It's not in joules.
It's in
Kilowatt.
Not quite. Close. Kilowatt.
Per second.
No. Kilowatt hours.
Hours.
KWH. Look at your bill. You're paying for kilowatt hours. Now, how do you get that? Well, what would happen if you multiplied work?
meter outside your house.
What's that?
Said, how they know that? I said, well, it's a meter outside your house.
Yeah. Okay. And let's call it energy per time. Multiply that by hours, which is a measure of time. This is kilowatt. Energy per time, that's power. Kilowatt. Those cancel out, and you're left with energy. So a kilowatt hour is a measure of energy. It's a much bigger measure of energy, too. Okay? A 100-watt light bulb run for, I don't know, let's just say an hour. That would use 100 joules. Because a watt, well, you'd have to do some figuring, okay? But it would come out being something like 1.8 million joules of energy. You think the power bill company wants to put 1.8 million on your power bill? No! People say, goodness, I use that much energy, I gotta shut back, you know? But see, a kilowatt hour is a huge amount of energy. But the numbers are pretty small. 12, 15, 150 kilowatt hours? Oh, yeah, we can pay that. But that would be several billion joules. No, they don't want to see a billion joules there, but they'll be paying for the same thing if it only says 150 kilowatt hours. So that, in my cynical view, is why they don't use joules. They use kilowatt hours. That's a lot of energy. A kilowatt hour is a lot of energy. Because a kilowatt is 1,000 joules per second. Multiply that by how many seconds in an hour. My word! There are 3,600 seconds in an hour. So multiply 1,000 joules by 3,600 seconds, you get 3.6 million joules in 1 kilowatt hour. No, they want to use kilowatt hours, they don't want to use joules. I'm sorry, I'm a cynic. Okay. That's what we're measuring. We're measuring not the power, but we're measuring that. But what is power? And what we said was joules per second. Or, yeah, watts. Okay? Now, what did we say a volt was? I've said it many times. A volt.
That's voltage.
Is what? actually, it's the amount of energy in joules per coulomb of charge. Remember, joules per coulomb. The amount of energy per unit charge, joules per coulomb. Now, what is current? Do you remember what that was? Was it too long ago? There it was right there. Q divided by T. Yeah, but let's use this one. Q divided by T. Q is the charge. T is the time. So it's Q divided by charge per unit time. Whoops, I'm going the wrong way. Close. Close. There we go. This is coulombs per second. So if we multiply joules per coulomb times coulombs per second, the coulombs cancel out, and what do we left with? Joules per second, which is a watt. A what? A watt. Yeah. Yeah, we got watts. So that's why, as you said earlier, voltage times current is equal to power. Okay. But you're not paying for power, you're paying for energy, which is the joules part, but we change that to kilowatt hours to make that bigger unit, smaller number. Okay. So let me erase my scratch here and see what they get to.
The formula for power is R times I squared.
What's that again?
The formula for power is R times I squared.
Okay, you're right on the money. You beat me to it. Here is power, which is current times voltage, right? But from Ohm's law, what was voltage? Ohm's law. I times R, okay? So instead of voltage here, if you put current times resistance, that's I squared R. Isn't that what you just said? Okay, sure enough, there it is. There's your another formula. Same thing, power, but now it's in terms, there it's in terms of current and voltage, there it's in terms of current and resistance. Now this leads you to something else. Anything that's using a lot of current is using a ton of power because you're squaring the current. And what is it that uses lots of current? Anything that produces heat. So the incandescent light bulbs at first have to heat up that filament, and you know when they've been on a while they're hot. Fluorescent tubes, they get hot, but not nearly as hot as incandescent. And the LEDs. If this were an incandescent bulb here, if I put my hand right there, I would feel the heat. Right now, I feel maybe just a little bit of warmth, okay? Because LEDs produce way less heat, so therefore the power is much less. So when you buy an LED, you save a lot of energy because if you'll notice on the thing, they'll say, because you see the light bulbs are all rated according to what the incandescents were, okay? And if you wanted a 60-watt bulb, that produced a certain amount of light, right? Well, if you bought that in a compact fluorescent, they would say 60-watt equivalent, meaning it puts out the same amount of light as a 60-watt incandescent bulb, but then in parentheses down there you would see probably it only used about maybe less than 10 watts itself because it was so much more efficient. Looking at LED, it may be 6.5 or something like that. I don't know the exact changes, but it's way less energy to put out the same amount of light. It's just amazing. Anything that produces heat. What's that?
Also, LEDs are a lot brighter.
Yeah, and that's because just a little bit of energy makes a really bright light. Okay, you're absolutely right. That's why they use them in these. They make such a good protection with hardly any energy loss. And the other really big advantage, those bulbs last a long time. Those old bulbs and the old projectors, they would be so hot and they would blow out really frequently, like sometimes every few months, usually, yeah. Right here, I can feel some heat coming out of here because this is generating some heat. If that was an incandescent bulb in there, I could hardly hold my hand that close to it. It would really be hot. Okay.
Why not melt some of that plastic off there?
What's that?
Why not melt some of that plastic off? too. They probably melt some plastic.
Yeah, and I've actually seen some of them that work. This is the intake side. You can't feel any heat there, but there's a little fan that blows across there. Because that is a lot of energy to make that bright of a picture. Okay. But think, your irons, your heater, your space heaters, your oven, your range, anything, clothes dryer, hot water heater, when those kick in, you can go out there and watch that meter box. You'll see that thing really start spinning when you use some of those devices. Other things like, I want to say TVs and things like this, pretty low amount for what you get. Now, some of the old TVs, if you felt the back of those TVs, those were hot. When they had transistors in the back, they put out a lot of heat too. Okay, things have gotten a lot more efficient, but as soon as they do, they get more devices, so you wind up using the same amount of energy. Okay, good deal. All right, I think we beat that almost to death, didn't we? All right. So, here's one more. Because I, from Ohm's law, what is I?
For Ohm's law?
Yeah. V divided by R, absolutely. So here, rather than I, let's do V divided by R times V, which is here already, and you get V squared over R. There's another power formula. Man, we got them coming out of our ears, don't we? P is equal to IV, P is equal to I squared R, or P is equal to V squared divided by R.
You want to do this lab today, or we cover it now?
What's that?
You want to do this lab today, or we cover it now?
The lab today is going to be back on Ohm's law. We just finished covering it.
Okay.
And we're still talking about it right there.
Right here.
Today's lab is going to be on Ohm's law.
Ohm's law, I did it.
Yeah, pretty good lab.
They can also equal to E times I, and also E squared divided by
It's
R.
a whole formula sequence.
E squared divided by, see, what you're calling E, we're calling V. Yeah, the potential difference squared divided by R. Perfect. Exactly. Okay? 3 different ways to express power. And of course, you could take the P equal IV and write 2 more equations that way. What would I be then?
So what?
Taking this equation, P is equal to IV, what would I be? IB.
Q divided by
P divided by V.
V.
Or if you took V, what would it be?
I.
No,
P divided by I.
P divided by I. So there's, man, one equation can give you so many, can it?
Yes, it did.
So look forward to
Too
them.
many formulas for it.
Second?
You got a lot of formulas too, huh?
Yeah. But you don't have to remember, just remember the main ones so you can derive all the rest of them. Okay. So let's look at energy, electric bills then. What you're paying for is not energy, is not power, you're paying for energy. Watts measures power. Time is measured in hours, so a watt hour or kilowatt hour would give you the energy you use. Then multiply that by the rate per kilowatt hour. That really should be per kilowatt hour, not per kilowatt. Yeah, well, that's okay, per kilowatt, yeah. And then, yeah. And then they divide by 1,000. Rather than dividing by 1,000 here, just write this in kilowatt rather than in watts, okay? But if you want to do it that way, it works too, okay? So, I think that leads to example 6.5. So let's back off and do example 6.5 here. I think we've got room. A 1,100 watt hairdryer. So 1,100 watts, what does that measure?
Power.
Power, exactly. Power is measured in watts. Watts, okay. is designed to operate on a 120 volt system. What's 120 volt? What is that a measure of? Voltage, or E, if you're like Brett. Some books and majors use E rather than V. That's what I always used when I was growing up too. How much current does the dryer require? So what are we looking for?
The current.
And what symbol is that?
I.
Capital I. And how is I related to P and V?
P divided by V.
P divided by V. You're absolutely right. So that would be 1,100 watts divided by 120 volts. What would be your current?
9.16.
9 point. Second? What did you get? 9 point what?
9.16.
16?
16 repeatedly.
And that, yeah. So let's call it 9.17. What unit for current?
Yeah.
Amps. Perfect. And what did they get? They said 9.2. Now, the reason they said, huh?
You get rounded too.
Yeah, what they did, they said there are only two significant digits here and here, so they made this 9.2. Fine, whatever. Okay, example 6.6. An electric fan is designed to draw 0.5 amps. 0.5 amps. So you see that's a lot less current than a hairdryer. Because a hairdryer produces heat, a fan just is turning a little motor. What's that a measure of?
Current.
Current, capital I. Okay. Electric fan is designed to draw 0.5 amps on a 120 volt circuit. 120 volt is measuring what?
Voltage.
Voltage, very good. Or E, if you're using that symbol. What is the power rating of the fan? So we're looking for power, and what is power?
Watt.
Yeah, it's in watts, but what would be the formula for it?
Current. Voltage.
Voltage times current. VI or IV. I like IV better, but it doesn't matter. So this would be 120 volts times 0.5 amps, and that would be how much? 60 watts. Okay, so an electric fan basically is about like an electric light bulb, 60 watt bulb. Doesn't draw much. Okay. Now, then they get into the cost, and you just have to work that. Now, before we get into that though, they have a pretty good little table here that summarizes a lot of your electrical units here, and they don't have it in slideshow, so I'm going to show it here. Charge, the symbol for that is Q. It's measured in coulombs. Capital C is a unit for coulomb. Okay, and the charge is the number of electrons times the individual electron charge, and that in there, 1 coulomb is 6.24 times 10 to the 18 electrons, or whatever your charges are. Okay. Electric potential, V, is energy per time or work per unit time. I mean, energy per charge or work per unit charge. So that would be joules per coulomb. That's a volt. Electric current is charge per unit time, coulombs per second. That's an ampere. Electrical resistance is volt per unit current, so that's a volt per amp, that's an ohm. And electrical power is current times voltage, which is a watt, which is a joule per second, just like we did before. Goodness, my hand is tired of holding that book up. All right, and then it gives some shocking costs here, though they're not, to me, all that shocking, but I guess he's making a play on words. Since Laria came in, and Michaela came in. All right, increase the class size significantly. We did have one other person here, but he left early. Yeah.
And also, like when you talk about resistor not only just determine like your temperature and all that, also run on a resistor has like you have your wire, you have like a round piece on top. Also there's like color code on there too.
Yeah. Now, for the lab today, forget your color code. We want to calculate our resistance, not read the resistance. What's that?
Colors like plus or minus 10, and
Yeah.
then silver is plus or minus 20.
Right. Yeah. And yeah, the resistors we'll use in the lab today have those color codes, but do the calculations and tell me resistance. Don't be reading the resistor. Okay. Yeah. I always have some that know a lot more about it than I do. And you sound like one of them. Okay. All right.
Our last all program we're going through is basically all electrical.
Yeah. Exactly. Yeah. That's what you specialize. Hey, there's Calvin here. We're finally getting a class here. All right. Wouldn't know we're having a test today by all the people here, would you? But anyway, there is a nice little blurb here on concepts applied, shocking cost. And if you want to look into those things, you sure can. I'll let you do that. And before we get to the next example, the people behind the science, as I've mentioned him several times before, you don't usually think of him as a person behind science, but he definitely was Benjamin Franklin. Okay? He was, it says here, the first great U.S. scientist. And I think that's a very good characterization. He, inventor, creative person, science, engineer, you name it. He invented what they call the Franklin stove, which was so much more efficient at heating a space like a home or a house or a store or something than was the old fireplace. Way more efficient, okay? He invented, he did a lot of the early studies with electricity, some of it at his own risk, but he was pretty careful with it and he never got electrocuted. So that was pretty smart of him. Really a great scientist. You can read this. This blurb cannot be your source if you choose to write on Benjamin Franklin. You'll have to use outside source, but this can give you plenty of good ideas. He was entrepreneur. He started his own business. He started the Pennsylvania Gazette, a newspaper, Poor Richard's Almanac, collection of articles and advice on a huge range of topics. He's just an incredible individual, okay? He started was highly involved with the first public library, invented bifocal lens for eye reading, so you can read and see distance through the same lens. Just amazing. Did studies on population control. I didn't know he invented the rocking chair. Really an incredible individual. And I think, unfortunately, he was responsible for daylight saving time. Okay? I don't really care for that one too much. Okay? It says, arguably the most interesting figure in the history of science, not only because of its extraordinary range of interest, but its central role in the establishment of the United States. Okay? Pretty incredible individual. Do all that. And he was one of the primary architects of both the Declaration of Independence and the Constitution. One of the few people who contributed largely to both of those. Thomas Jefferson is given most credit for the Declaration of Independence, but Franklin was on the team that put it together. And then Thomas Jefferson was completely out of the country when the Constitution was being written, so he wasn't much involved with that at all. But interesting character. A good paper topic if you're interested. Let's do example 6.7. I think I'm going to erase what I've written here. This is on page 155, by the way, for people who just got here. What is the cost of operating a 100-watt light bulb? So here we have a 100-watt light bulb. That's a measure of what? Power. Okay. For 1 hour. That's your time, 1.00 hours. That's your time. if the utility rate is 10 cents per kilowatt hour. So the rate is, I'm going to write it this way because it's the way the book does, and also it makes more sense later. 0.10 per kilowatt hour. 10 cents per kilowatt hour. Now I can remember back when my wife and I first moved here to Alabama, this was about the late 80s. I can remember Alabama Power advertising on television that they had some of the lowest utility rates in the country, as low as 7 cents per kilowatt hour. Look at your bills now, I bet you that's nowhere close, okay? Probably 3 times that, if not more, okay? But this one says 10 cents per kilowatt hour, which is a pretty low rate too, okay? So we want to know what the cost of operating that 100 watt bulb for 1 hour would be. Well, 100 watts times the 1.00 hours would give you, 1 times 100 is 100 watt hours. Pretty simple to do, right? And since the cost is 10 cents per kilowatt hour, it's really easy to make that into kilowatt hours. How do we change the watt to a kilowatt? Divide by? Okay, I'm not saying that. You're in the same unit. Watts and kilowatts measure the same thing. So how do you go from 100 watts to so many kilowatts? Kilo means 1,000. That has 3 zeros to divide by 1,000. In other words, move your decimal 3 places to the left and change that to kilowatt hours. Because kilowatt is a bigger unit, so you need a smaller number for the same thing here. So that's 10 cents. So now you got kilowatt hours. Take your 10 cents, 0.10 cents per kilowatt hour, and multiply it by 0.100 kilowatt hours. Now your kilowatt hours go away, and that gives you 0.01. 1 cent is how much that 100 watt light bulb costs you to burn for 1 hour. Now that's at 10 cents per kilowatt hour. I bet you we're probably close to twice that now, okay? So we're probably 17 or so cents per kilowatt hour, cents now. But still, it's pretty cheap. But that's off 1 hour. If you just do it 1 hour a day for 30 days, that's 30, okay? So that would be the 30 cents or whatever. And then, it can add up, okay? Now I'm sort of the light Nazi in this building, actually when I'm on Birmingham campus too. If I walk by a classroom and there's nobody in there, I'll turn off the lights. I do it at home too. It makes my wife mad, but it's just I don't see running the lights. Even though it's not costing very much, I understand that. But why cost anything if no one's in the room? So it's just me. Okay. Let's do example 6.8. An electric fan draws about 0.5 amps. What's that a measure of? Current. What symbol is that? I. Okay. In a 120 volt circuit. 120 volts measures your voltage. That's your V, or Brett uses E. That's fine. What is the cost of operating the fan if the rate is 10 cents per kilowatt hour? So again, your rate is 0.10 per kilowatt hour. Okay? Well, what can you get out of the fact that you have a current and a voltage here? What does that give you? Power. How does it give you power? What is power? I times V. So this will be 0.5 amps times 120 volts And what does that give you? 60 what? What? Watts. Okay, 60 watts. Okay, we want it per kilowatt hour, so we want to change this watts to kilowatts. So how would you do that? How many places? 3 places. So you have to put a 0 in front. That's 0.06 kilowatts. Okay? So multiply that by 0.060 kilowatts. And the kilowatts here cancels kilowatts there. So that would give you 0.006 cents. That's 0.6 of a cent per hour. That would be the rate at which you're using energy. 0.6 of a cent per hour for that electric fan. That's not very much, okay? And in fact, fans are usually pretty good things to use as far as energy conservation. If you can operate a fan and cut back your air conditioning, you're going to save a lot of money, okay? Because the fan will, in a sense, feel like it's cooling you off almost as well as the AC will, okay? Not as good, but almost as good. And it can save you tons of money because those AC, the first step in the air conditioning system is compressing a gas that's creating heat. You blow off the heat and then expand the gas, and that's what gives you your cooling. Well, that step of producing the heat, that's costing you big bucks. Okay, so that's example 6.7. Now we're ready to move to magnetism. So this chapter I always thought should be called electricity and magnetism. It was only called electricity, but pretty close to half the chapter is magnetism too, at least the part that combines electricity with magnetism. So what is magnetism? Well, the earliest ideas we just observed, and we saw that there were some naturally occurring magnetic materials. The common name for it was lodestone, Lodestone. The mineral name for lodestone is magnetite. Okay? Chris is here. Now, interesting thing about magnetite, it is an iron ore, okay? And there's another iron ore called hematite. Chemically speaking, they are identical. There is no difference. The only difference is magnetite is naturally occurring magnetic, hematite naturally not magnetic. I mean, it can be magnetized, but it doesn't occur that way naturally. Exactly the same mineral, exactly the same chemistry. It's just one's magnetic and one is not. They both can be made magnetic, but one. Now, here's the deal about magnetism. If you remember when we were talking about electrical things, we have either positive charges or negative charges. What was the rule about positive and negative charges?
They attract you.
Yes, positive, unlike charges attract, and
Like charges.
charges repel. Whether positive, they repel. Negative, they repel. Well, in magnetism, there's some similarities. You don't have charges, but you have poles. And we call these a north-seeking pole or a south-seeking pole. Now, most of the time we leave off the seeking part and we just say north pole and south pole. But really the better term would be north-seeking pole and south-seeking pole. And guess what the rules are with them? Like poles, repel each other. Unlike poles, attract each other. So a north and a north, push away. A south and a south, push away. A north and a south, pull together. Okay? So same type of rule that you had in electric. One big difference though. You could, in electricity, have an isolated positive charge, no sweat. You can have an isolated negative charge, no sweat. How about with magnets? Can you have an isolated North Pole? No, you can't. Now, some people have tried. So let's say we got a bar magnet here. North Pole, let's do the North Pole, South Pole. Okay? Well, let's just cut it in two and isolate the North Pole from the South Pole. Okay, back up a minute. How you can test the magneticness, I guess you would say, of that bar magnet is put a piece of paper over the top of it and sprinkle iron filings all along it. And if you do that, you'll find that the iron filings all congregate at the poles. North Pole, South Pole, in the middle, hardly any will congregate. They all move to the poles. Okay? And they stand up there. I mean, they just are really crowded there. So let's take that bar magnet and cut it in two, break it in two, any way you can get it in two. Isolate the North Pole, right? Guess what? As soon as you break it into this part in the middle that was not magnetic much at all, suddenly it becomes a South Pole. And this part over here, that part becomes a North Pole. Sprinkle iron filings on that. There they are, and there they are. You cannot isolate a monopole, a pole that's just north or south. No matter what you do, you're going to have a north and a south pole. Now, I bet you some of you, probably most of you, have on your refrigerator at home a little thing that's magnetic, don't you? Any of you? Anything stuck to your refrigerator that's magnetic?
Yeah.
Calendar? Yeah, something like that. If you look at the magnet there, those magnets are about that thick, aren't they?
Yes.
One's a North Pole, one's a South Pole. If you cut it in two, you'd have the North and South and the North and South. You can't isolate a North Pole or a South Pole. You cannot isolate a monopole. Okay? Now, there are only three naturally occurring magnetic materials: iron, cobalt, and nickel. These are called the ferromagnetic materials. Ferro meaning iron, that's what the symbol for iron is, Fe. Cobalt and nickel are two others. And the interesting thing, and it's not a coincidence either, I'm convinced, if you look at your periodic table, which should be in the back of your book or somewhere in your text, look at the periodic table and you find iron is down here at number 26, and just to its right is number 27. Cobalt, and just to its right is number 28, nickel. There they are. Those three are the only naturally occurring magnetic materials. Now, we've been able to fabricate others, but just about every one of them is going to have either iron, cobalt, nickel, or some mixture of those together. In fact, one I read about last night was some sort of nickel. It's called alnico, which is aluminum, nickel, and cobalt. Aluminum is not magnetic, but when you combine it with nickel and cobalt, sure enough, you get magnetic material. So you can create other alloys that have other characteristics that are also magnetic. But you almost got to have either iron, cobalt, or nickel in them to be magnetic. Okay? Now, in the old days, all they knew about them were these naturally occurring things, lodestone, naturally magnetic. You see other materials stuck to them. That's how they knew it was magnetic, okay? And so, well, if you take that and stroke a needle on that naturally occurring magnet, then that needle, put it in water, it's going to point pretty close to due north. Not exact, pretty close. That's what they're used for, making compasses. So the sailors out at sea could know where north was, and then they knew which way to steer to get where they needed to go, okay? Because compasses always pointed approximately to the north. That's about all we knew about them. They were a very useful thing to know. Because out at sea, there aren't any landmarks. Everything looks the same. Every horizon looks the same. And here's Landis. Okay. All right. The modern view, then, is that magnets, magnetic forces, they're associated with magnetic fields. Just like gravitational forces are associated with gravitational fields, electrical forces associated with electrical fields. There are always fields involved. The field lines go, and here's just the convention. Remember how they went for electrical fields? The field lines always go away from positive charges toward negative charges. Okay? The modern view, the field lines with magnets, the field lines always go away from the north toward the south. Always. Okay? Now, the magnetic fields and the poles are absolutely inseparable. You can't separate them at all. Okay? Somebody else here. Okay, we wound up getting a reasonably good class. Numbers, always good in people. The poles always, this is what I was saying before, always come in north-south pairs. You cannot isolate a monopole. They always come in pairs. Okay? No matter how many times you cut that magnet in two, you're still going to have 2 magnets, 4 magnets, whatever. The field lines, this is what they were saying before, always go away from the north poles and point toward the south poles. Like magnetic poles repel, unlike magnetic poles attract. North attracts south, south attracts north, north repels north, and south repels south. Here's the illustration of what I was just talking about. If you had this bar magnet to begin with, sprinkled iron filings, they're all going to congregate at the poles. All of them, pretty much. I mean, a few scattered other places. Most of them at the poles. You break that in two somehow, saw it in two, somehow get it into 2 pieces, and now suddenly you made a new north here and a new south there. You put the iron filings there, they congregate here, and they congregate here. No matter what, you cut them again, here, 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 here. You cannot isolate a north or a south pole, a monopole. They always come in pairs. No matter how many times you break it, that will happen. Okay? Here's an illustration of the field lines. And again, the convention is the field lines always go from north toward south. From north toward south. Point in that direction. Why do we determine that? We take a little magnetic compass and we put the magnetic compass here, it's going to point that way. Here, it points that way. Here, it points that way. Always pointing away from north toward the south. So therefore, we do that as the field lines. Okay? Notice how the field lines are thickest around the poles. That's where the strength of the magnet is. Thinnest in the middle because they're really spread apart there. The concentration of the field lines indicates the strength of the magnetic field. Make sense? All right. What is actually the source of these magnetic poles? And by the way, here's a pretty strong magnet with stuck near iron filings. Look at those things. Look like a hairy beast of it. Someone wiped away these so you can see the north and south, but none congregate down here. They all congregate right around the poles. And if you were to break this in two, suddenly they congregate here and here, here and here. You'd have 4 poles rather than 2. Okay? So, what's the source of these magnetic fields? Well, this really gets into some deep stuff that I can't say I even fully comprehend, but I certainly would have a hard time trying to explain even that which I thought I understood. Here's what's happening. I've said this before, I'm going to say it again. Magnetic fields exist where there are moving charges. Magnetic fields exist when you have a moving charge. So therefore, if you have some of your subatomic particles, like electrons or protons, moving. Now, most of the time, protons don't move very much. I mean, they may have some little vibrations and stuff like this, but not enough to create big magnetic fields. Electrons are moving always, okay? And they're doing all sorts of things. They're spinning, they're moving around, they're doing all sorts of things. Well, every element out there, every atom out there has electrons moving all around, spinning and moving and stuff like this, but all of them don't produce magnetic fields. Only 3 produce magnetic fields. What are they? of three naturally occurring magnetic materials. Long time ago, we had the slide.
Iron, cobalt.
It's smaller than a dime.
Yeah.
Nickel, very good. Okay, very good. Okay. Iron, nickel, and cobalt. Those are the only three. Okay? Well, what must be happening? Well, there's orbital motions in the electrons, in the atoms, but most atoms aren't magnetic. Well, what is happening? We have macroscopic fields that are in permanent magnets, Earth's magnetic field, electric currents, electromagnets. We have these, but what must we have in our nickel and cobalt? It must be in every other atom. The spins are just all over the place. But in iron, nickel, and cobalt, they must go a little bit more regularly in just one dimension, making a magnetic field. Okay? But not all iron, nickel, and cobalt. For instance, hematite is not magnetic because its individual fields, there are some like this and this and this, so they all cancel each other out. But in magnetite, they more of them line up with each other, making naturally occurring magnets. We're going to get to that part later. So macroscopic fields are the big thing, things that we can measure, exist either as permanent magnets. We'll use some of these in lab next time. Earth's magnetic field, we'll measure that using our compasses and stuff, and we'll do that in the next lab too. Not today, but the next one. Electric currents produce magnetic fields. A moving charge produces a magnetic field. This is from electromagnets. We'll see that. So let's take these individually, okay? And let's look at permanent magnets first, okay? Here's what we're talking about. The only way you can have a permanent magnet is for Rhodesia to get here, okay? And she did. All right. Anybody else come in since I called off? Okay? Has to be ferromagnetic materials. What are they? What are they? Ferromagnetic materials? Only three of them.
Oh, cobalt,
Iron, nickel, and cobalt. Very good. Those are the only three. Any other material, try like you might, you're not going to make them magnetic. They won't become magnetic. Okay, so you have to have ferromagnetic materials, number one. Iron, nickel, cobalt, or some combination of those. Alloys or whatever. You have to have this atomic magnetic moment. That's the electron-proton intrinsic moments or electron orbital motion, something there to create the fields. Only iron, nickel, and cobalt have these in large quantity. Now, you have to have clusters of atomic moments aligned within domains. Now, this is a little bit squirrelier concept, but let's just say in the ferromagnetic material, you have these clusters. Now, here's some clusters pointing up, but you have other clusters pointing down, up and down, left and right, right and left. So guess what? This iron, nickel or cobalt, not going to be magnetic. You can make it magnetic, but it's not going to be magnetic itself. It's going to be neutral. Okay? But what if you place this in a strong magnetic field? In other words, here's a North Pole, maybe over here somewhere is a South Pole, or just the North Pole here, you put it in there. Now some of these clusters start aligning with the magnetic field here, and you've induced this into becoming a magnetic material. I mean, it's already was magnetic, but now it becomes a magnet because its fields are now, it's magnetized because the domains align. So how do we make that happen? Well, I'll give you a dumb example, but this really happened to me. I just couldn't believe it. I wasn't expecting it. It snuck up and happened, then I realized what had happened. Told you all the story of digging the patio in the backyard, right, and the power and all that kind of stuff. Well, actually, before I started digging that, we had just bought the house, and there was a rickety old privacy fence. We had the garage here, then there was a tool storage shed in terrible shape, rotting, okay, uneven, falling apart, dangerous to be in, but that's where they had been keeping their tools. And then attached to that, back to the corner, was an old privacy fence, in pretty bad shape, okay? Well, I had to get rid of this tool shed because it was literally, you'd step on the floorboards, they'd break through, you're afraid the ceiling was going to cave in on you, it had nails in it, just wasn't safe, okay? And also, when they had surveyed the land, I found out the property line was 4 feet over into the neighbor's yard from where we were. They had just gone from the back of the garage and gone to the corner. So they were moving 4 feet of our yard, that made our yard smaller. So I talked with the lady. She was renting, so she called the landlady. Said, yeah, they knew that was over, but that's just where they put the fence, so they just kept it that way. I said, well, I've got to move the shed, so I was going to move the fence. Fine, do it. Okay, so we did. So I had to put up new posts for the fence. So take out that shed anyway, and then put up new posts for the fence, new privacy fence. And so I was doing this, and it's on a hillside. Remember, the yard is on a hill. So I had the post at the corner. I knew exactly where that was. That's where the stake was. I knew where the end was down here too, and that was just past the garage here. So I lined up and planted the post at that corner and this corner. And then I ran a string between that, and I was going to plant the other posts along that string, to keep them in line. Well, I'm not a very good hammerer, but I was standing down there hammering way above my head because you see the base of that post was up on the hill. The top of this post I was trying to get fairly level with that. So I was trying to hammer the nail in here so I could tie the string around it so I could plant my post. Well, I'm not a very good hammerer, and when I was doing that, the nail popped out. And I started looking around in the leaves and the grass, just happened to hold the hammer down here with it, just because I didn't want to leave it up there somewhere. And suddenly the nail went to the hammer. I said, what? It went to the hammer. And I said, what happened here? And then I realized, thought about it, I was hammering just about going due north. I mean, almost perfectly due north. So I was aligned with the Earth's magnetic field lines while I banged on that nail, metal, iron nail with an iron hammerhead. Okay? So I actually shook up these domains in the presence of the Earth's magnetic field and made the iron, the hammerhead, and the nail magnets. So that's when I was down here looking for the nail, scratching around, it found the hammerhead and went through it. It had become a magnet because I perturbed it in the presence of a magnetic field. Not a very strong field. The Earth's magnetic field is not that strong, but it was strong enough that it attracted the nail. It got close enough to the nail. And sure enough, that can happen. If you've ever stroked a nail or something like that on a strong magnet, it becomes magnetic. And that's how they used to make the compass needles. They'd find a piece of lodestone, stroke a needle on it that was made out of iron, and then it would float in water and point to the north. Okay? That's how they did it. Or float in some liquid. So that's how you get your magnetized domains to align. Non-magnetized, they're randomly oriented, they cancel each other out. When they're not randomly oriented, aligned with a magnetic field, that's when they become magnetized. That's why some iron is magnetic. I mean, it's all magnetic, but some is actually a magnet, other is not. Okay, how are we doing on time? Maybe time for this one slide. Earth's magnetic field. That originates deep, deep inside the Earth. Okay? Michaela and Zaria could tell you, and so could Seth. Oh, yeah, you were in the last class too, weren't you? Yeah, okay. Lots of you could tell about the Earth structure, couldn't you? You have an inner core that's solid. Then you have an outer core that's liquid. And then you have the mantle that's on the outside, okay, and then the crust is just the very thin shell there. And the earth is spinning, right? And the core, much of the mantle, but just about all the core, is mostly what two elements? The core of the earth and the mantle, mostly what two elements? Any of you remember? Iron and nickel. Iron and nickel, mostly iron, but it has a large amount of nickel too. And guess what? Naturally occurring ferromagnetic materials, iron and nickel. There's not much cobalt there, but there's iron and nickel plenty. Well, that's spinning. And that mantle of the earth is spinning with every spin of the earth. It spins because it's solid. The liquid that's inside, it doesn't spin as much because it's liquid. It just sits there, right? And when those two are happening, and that inner part of the mantle is not a nice smooth shell, it's ragged and jagged and all that kind of stuff. So it's always knocking electrons off the iron in the liquid core. And in so doing, it's setting up movement of charge. And anytime you have movement of charge, what do you have? A magnetic field. A magnetic field. So that's what's happening. It originates deep beneath the surface, down at the place where the molten core, the liquid core, is bumping against the solid mantle. Okay? So that makes a magnetic north pole, which is actually acts like a south pole, which is bizarre if you think about it, because all the other compasses are pointing toward that. That must be really a south pole, or else you call the compass needles a north-seeking pole. Either one, but in other words, the magnetic dipole is there. Okay. Now, one problem with it. Let me show you on the map, on the globe. The true North Pole is the axis where we spin, right? That's the North Pole. If you have a gyroscope compass, it's going to point to the true North Pole, because that's based on the spin of the Earth. However, the magnetic North Pole is not quite there. The magnetic North Pole is right there, off by, let's see, what is that? About 20 degrees off from the true north. The south magnetic pole is even worse. Okay? There it is. It's more than goodness, I can't find it here. But it's actually outside the Antarctic Circle. So it's quite a few degrees off. Still close, really close, but not quite the same. So therefore, since there is a little bit of an offset there, therefore your magnetic compass is not going to point quite to true north. Close, but not quite. And we call that offset the magnetic declination. Okay? And here is the strangest thing I think I've learned in any of these courses. The direction of the magnetic field periodically reverses itself, and I cannot, for any part of my imagination, come up with an adequate reason why. Okay? It doesn't happen often, about every million years or so. Okay? So we don't have to worry about it. It's going to be north most of our lifetimes, in fact, all of our lifetime, but it will reverse itself. Now here's the other fact, and they get this from studying the pores of rock as you go down in different magnetic deposits, volcanic deposits. You'll find sometimes the lodestone, the north is pointing this way, sometimes it's pointing that way, sometimes this way, sometimes that. In between that, you don't find much lodestone. So what I think is happening is it's a very, very slow sinusoidal thing. Sometimes it's this way strong, sometimes it's this way strong, but other times it's weak to non-existent. We just happen to be living in a 700,000 year period where it's been in one direction and relatively strong. Actually seems to be, I think they say, getting a little weaker every year. So we may be approaching a time when we don't really have much magnetic field of the Earth. I still can't figure out why, but it seems to follow some sort of sinusoidal pattern. Okay. Now, what's the result of this? That means if you have a magnetic compass at different parts of the country, it's not quite always pointing due north. Fortunately, the place where we line up the magnetic North Pole right here, right there, with the true North Pole happens to be a place that cuts almost through Atlanta, Georgia, a little bit east of Atlanta, Georgia, maybe Athens, Georgia, or somewhere around there. We're not far from that at all. Here's Birmingham, and I can't read that map. We're about 2 degrees off. That's not bad. Not bad at all. Okay? Over here, just east of Atlanta, you're almost dead on. Your magnetic compass is going to point almost exactly true north. Birmingham off by about 2 degrees. Over here in Meridian, maybe 4 degrees. Over here in New Orleans or Baton Rouge, 6 degrees off. Down here in Galveston, Texas, or near that, maybe 8 degrees off. Over here, maybe Arlington or Austin, Texas, maybe 10 degrees off. Over here in, say, Santa Fe, New Mexico, somewhere around in there, close to 12 degrees off. So you see, the further you get, the more off you get because you get greater differences between that. Up here in maybe Myrtle Beach, North Carolina, that looks to be about 6 degrees off. Okay? Up here around Baltimore, Maryland, or somewhere around in there, you may be, I can't read that, 10 degrees off. Okay? Up here around Maine, southern Maine here, you could be 18 degrees off. So you see, it varies depending on where you are. We happen to be in an area that very little deviation, magnetic declination. All right. Now, it's about time to start lab. It looks like to me we went to a pretty good place here. 6.4 is electric currents and magnetism. So this is the part where we're going to start tying electricity with magnetism. Okay? Magnetism part wasn't that big. The rest of the chapter is going to be tying electricity with magnetism. The next lab, the one we do on Tuesday, hopefully we'll get enough done to do that, is called electromagnetism. We're going to look at both of them together. So that will be beginning with 6.4 on page 159. And we don't have that much more to go. There's a fair amount. It's going to take us most of the time, maybe not all of it, to get that done on Tuesday. Now, those who weren't here early, let me go over just a few things here. We have class today, lab, and then a test. Chapter 4 test is the last 30 minutes today, so if you don't have your formula equation sheet together, be getting that done. Okay? So that's today. Tuesday, we hopefully will finish chapter 6 and maybe even start chapter 8. We probably won't get too far in 8, but we'll get started in chapter 8. Okay? Then Tuesday, the last 2 hours, we'll have the lab on electromagnetism. All right. Thursday, then, of next week, we will continue chapter 8, and if we do finish chapter 6 on Tuesday, the last 30 minutes on Thursday, we'll have the test on chapter 6. We do have class the Tuesday after everybody else has started finals. We don't, okay, because this is a mini-term class. We have class Tuesday, I think it's the 30th of April, okay? On the 30th of April, we do have class. Hopefully in that class, we'll finish Chapter 8 and then have the lab for Chapter 8. Now, that may take most of the class period. If it doesn't, if we finish the chapter and finish the lab, and you want to do your Chapter 8 test, I don't usually give it the same day we finish the chapter, but if you want to, you can take the test that day. Otherwise, the Chapter 8 test will be on Thursday, and your final exam will be on Thursday. So we'll wait till next week and see how we finish. But if we do finish in time, and some of you want to go on and take either the Chapter 8 test or both on that Tuesday, if we have time, you can do it. If we don't have time, both of them will be on that Thursday. Okay? We'll wait and see how it pans out. But that's technically when your final exam is Thursday, which I think is the 2nd of May.
Yeah.
Okay. That's when now actually what they say on the final exam schedule, they say all mini-term 2 finals are on Monday the 6th, which is nuts, okay? Because what if a student is taking more than one mini-term courses? Then all their finals are on the same day. And what if you have a Monday-Wednesday class at 1:15 in the afternoon and a Tuesday-Thursday at 1:15? What time on Monday are you taking your exam? You can't take them both at the same time, so that's nuts. And some of you may be working or other things like this that you can only be here on Tuesday and Thursday, so why make you come in on Monday to take the test? So I'm going to give you a test, unless we finish early, which I don't think we will, but I'll give you the option if we do. The final will be that Thursday. And we'll wait until closer to that time to talk about whether we have pizza or not, which day. But usually we have pizza at the end. So that's just neither here nor there. Okay. We'll talk about that later. Any questions on what we covered so far in Chapter 6? Yes?
Will the final that Thursday start at like what time class normally starts?
Unless there's a conflict. Do you have another final that's sometime on?
No, I have one from 11 to 1. I just wasn't sure if there was like a specific time that we had to take finals. Because I know other classes.
It's not a fixed time. I was just figuring to do it at a regular time.
Okay.
But if you're in another final, just come on whenever you can get here. Okay. Because I'll be here from 1:15 till 5:45, actually till 6 o'clock comes out. Anytime during that time period. Now, if we're going to have pizza, it may be cold by the time you get here if you don't get here on time, okay? But that's your problem. Okay. I didn't say that, did I? Not out loud. All right. I'm going to pause the recording. All right. Excuse me. Excuse me? All right. Sorry that it took longer to set up than I thought. I didn't know I was going to have to move all the stuff from that lab to this lab, but they were doing some sort of lab final or something in there, so couldn't do it. So what you have here, your procedure on page 194. Yes? Yes, I did. Thank you. Appreciate it. Yeah, I turned it on. Hopefully it'll pick me up. Okay? I have a setup here similar to what you see on page 194. We have the adjustable power supply, which is the box on the bottom, the blue box on the bottom that we used last time. Connected to that is an ammeter, which is the little box on the side. Okay? It goes over. Now, we don't have a voltmeter listed here because the voltmeter on our box is telling us the voltage. Okay? And then we have the load, the resistance, which is the resistor that's up here on top. Okay. Now,
we need to color code it.
What's that?
We need to color code the resistance.
No, don't worry with that at all. Okay? We're going to calculate the resistance. Okay? Not read it. Okay? So what you're going to do, turn on your, okay, listen, before you do it, what you're going to do is turn on the power supplies, the red button. Okay? Now, don't yet. Okay? Now, I have it set up to be close to 1 volt. It may not be exactly. These things drift a little bit, and I just got close to make sure I was on the right scale. That's going to be in volts, okay? Tenths of a volt. It's going to read to the nearest tenth of a volt. So what I want you to do is, when you turn it on, get it as close to 1 volt as you can, and then read the ammeter. Now the problem with the ammeter, it's in milliamps, okay? And what you're going to record on the table, and this is on page 197, you're doing 197 first, not 198, so be sure you're on the right page. You'll record the voltage you have, and then the current, but it says the current in amps, so you've got to convert milliamps to amps. Okay? Now, someone turn it on real quickly and give me a reading of milliamps.
9.08.
Okay, turn it off then. Now, if that's what you happen to get, I'm not saying that's going to be your measurement, 9.08.
Yes.
That's milliamps. What would that be in amps? Anybody?
0.09.
More than that.
9,000.
That's going the wrong way. 0.009. You move the decimal 3 places to the left.
Oh, to the left.
00908 or whatever. So that's what you record in amps.
So 0.009.
That's what it would be. And whatever units you got there. Use all the digits you got. Okay? So once you have set it for 1 and measure the current and put it in amps, then set it up to 2, do the same thing, or as close as you can to 2, 3, 4, 5, and 6. So try to aim for voltages 1, 2, 3, 4, 5, and 6. If you can't get 1 on the nose, and it's 0.9 or 1.1 or 1.2, write down what the voltage is, write down what the current. It'll all take care of itself, but get what you're actually measuring. Okay? Any questions? All right. I'm going to steal a stool if it's okay. Now, if you have any questions, please ask. I'm going to put the recorder on pause for now because it's... Okay. Now, some of you have completed the first set. Okay.
You got to do on this side.
You're still working. Wait. Huh?
You got to do on this page too, or no?
Yeah. You don't do a thing there until I tell you.
All right.
Okay, you got this. Okay. Now, what you're doing, you recorded the value of the, 6 values for current and voltage on the table, data table 22.1. Everybody did that. That's on page 197, or you're in the process of doing it, right? Okay. Now, what you do next is go down to results and make a graph of the 6 data points from table 22.1, placing the current on the horizontal axis and the voltage on the vertical axis. Now, tell me about the range of your the voltages are 1 to 6, of course, and your currents are about equivalent. So
they're like 9 to 59.
Okay. So since it said the current on the horizontal axis. Okay. Now you got 2 graph sheets. Do it on the first graph sheet, and your current. Yeah. The current you'll do horizontally. So set it up in letter mode like this, and your currents are basically 0 to 6. Oh, right, approximately?
Yeah.
Yes.
Okay. So 0, 1, 2, 3, 4, 5, 6. Fits on there perfectly.
All right.
Okay? Now, your voltages, only these are milliamps, so what you're going to do is not 1. Okay, it's going to be 0.001, 0.002, 0.0... Huh? Current. That's the current. Okay, 0.001,
I'm confused.
0.002, .003, .004, .005, and .006. Right? Isn't that about what your currents are going to?
No.
What are they going to?
Mine's going higher. That's my current.
Oh, okay. I'm sorry. .0. Just 1 0. Take that back again. Okay. .01, .02, .03, .04, .05, and .06.
And this is the voltage?
No, that's your current on the horizontal scale. Right? That's what you told me. Is that what everybody got? Something?
It's the current rate.
Yes. And it's going from about .01 to about .06.
Oh, yeah.
Right?
You're right.
.01, .02, .03, .04, .05, .06. Everybody data match that pretty close? Yeah. Yay or nay?
Yes.
Okay. Your voltages are then going to be, okay, 0 at the bottom, 1, 2, 3, 4, 5, and 6. Okay? And if you had a decimal 1 or 2 above, then you got nearest tenth here. So that should be no problem plotting those points.
All right. And then just graph it. Yes.
Okay? Then, yeah, plot the points and then draw. And here, every team, you have 10 people here. There's 10 rulers. 3 for this team, 3 for this team, and 4 for this team. It works out perfectly. Get your ruler and go the best straight line through all the points. Don't zigzag. Make the best single straight line from the 6 points. If you want to and can, if it fits, use 0, 0. Because if you had 0 volts, you'd have 0 amps. So if that fits, use it too. But if it doesn't fit, use the 6 that you plotted. Okay? Does that make sense? All right. Work on that then. And when you get that done, let me know. So it's a quick review of where you are so far. You did Part A, known resistance. You recorded the value of resistor and 6 values of current and the voltage in the data table. Okay? And then you made a graph of the 6 data points, placing current on the horizontal scale, the voltage on the vertical scale. We talked about what range to put there. And it says calculate the slope and write it on number 1 on page 194 and somewhere on the graph. Everybody done that?
Yes.
Calculate the slope and write it there. Okay? Has everyone done that part? Or are you still working on your slope?
All right. So, be on number 2.
Okay? Yeah, number 2. Have you calculated your slope?
Yes.
What did you
Oh,
get?
you got what the slope.
Okay? Show me the graph. Rise over run. Okay? Now, your points are really close, so I would do the change of your voltage here between this one and that one. That should be pretty easy to calculate. Okay? Then divide that by the change of the current, this minus that, whatever those values were, and then you do your division. All right, y'all ready to keep going? Okay. I've set you up a new resistor. So turn it back down to close to 1 volt.
This thing goes crazy.
I know, one of them does. Okay. You have to be very.
I mean, like, you can barely turn it
I
and
know.
it'll shoot up. And then it shoots back down.
Yeah, it's really. That may be as close as you can get. Okay. Now, yeah. Okay. And do the same as you did before, but register not 1, but whatever your voltmeter reads, whatever your ammeter reads. But you got to change your amps to milliamps to amps.
Yeah.
Okay. Y'all calculate your slope yet? Yeah. What you get? Okay. Calculate what that is.
Tell you what happened to the slope.
That's a good
No, tell you don't have it.
Okay, record that on your graph and on the.
Yeah. All right.
Okay.
It's 0.005.
Okay.
Or 0.0050.
Pretty close. You can either use that one or this one. And this one's right on. So change the voltage here, whatever that is, minus whatever this one is. Okay? That's the rise. The run is whatever the current is here, minus the current there. You got those on your data table, which really should fine. Then do the division. I did. So you start over at 1, 2, 3, 4, 5. Okay. So you've got your new resistors in. Start reading again. 1, 2, 3, 4, 5, 6 volts, and read your amps. The currents are here now. Going from approximately 2 to 610. You say it's just
Yes.
Yeah. From 2 to 610. So, and that's actually 0. To about. So let's do 0.0, 0.0369.
Point zero
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 zero three.
006. Okay.
06, yeah. All right, let me see. 6, 9. Yeah, that will work.
Okay. Hold on. Let me see.
And how did you get the bottom?
Okay, that's the chain. Okay. You always is high minus low, not low.
Oh, I'm sorry. It's the same 5.1.
Yeah, okay. Okay, then flip over. Right, so the difference between this and that. Two. Very good. Now, start doing with the new resistor I put in there.
Okay. Good. Okay. I know. Now we done with that. We do the same thing in the next page. I'm with these. Okay, so drop the one.
You said it in my.
What's that?
That looks bad,
Okay.
but
What's your, did you calculate last month?
not yet. Which one's?
Well, just looking at this, it looks like this point and that point are both on the line side.
For real? My pastor did too. He said, I don't get money like that. But I think it's lying. Yeah. My mom, I couldn't work. I was talking about Lord had my face do in that house. You got to same shit. Grab.
It's really hard. Okay. Now.
Okay, now I'll go back and tell you the rest of it. I want to let them get far enough along. Okay. All right, I'll do it. Second Sunday. You might hear sirens going off in the knee. So you turn off your thing there. Did y'all turn off your light? Oh, no. Okay. Is everyone through with their electrical components? Okay. I've seen everybody's first estimate of slope. I haven't seen everybody's second. As soon as you've got a second slope, let me know. Okay, now we're not listening. Okay, maybe you'll still get it. You needed to change scales on the second. So it's okay. Oh, I'm still recording. Sorry.